Hello, this is the fourth video of the first order differential equation series for OCR Pure Core Further Mathematics, and it applies the separation of variables method. We will revisit the example in the previous video where Newton's law of cooling states that the rate at which an object cools is proportional to the amount by which its temperature exceeds that of its surroundings. If a room has a constant temperature of 20 degrees C and a cup of coffee at a temperature 80 degrees C is initially cooling at a rate of 5 degrees C per minute, we want to know how long it will take the coffee to cool by 20 degrees C. In a previous video, we already identified that dt, where capital T is for temperature, by d small t, where that is for time, equals minus k T minus 20. So we can see that the rate of change is not constant, as it depends on the temperature at specific times. And therefore, because it's not a constant rate of change, we can't simply divide the 20 degrees C by the 5 degrees C per minute to get 4 minutes. Using this model, let's see what other information we've got. We know that initially, at T equals 0, the temperature is 80 degrees C, and we know that the rate of cooling, so dt by dt, will equal minus 5, and we say it's negative 5 because it's cooling. If we substitute in these values, we can see that at the time t equals 0, we will find that k equals 12. So, having started with our model, we've now worked out the value of k for the given conditions. We can now apply the separation of variables method. And you will see that we will then integrate 1 over t minus 20 dt will equal minus a 12th of dt. This gives us log t minus 20 equals minus t over 12 plus our constant of integration, which we'll call c. Taking the exponential of both sides, this will give us t minus 20 equals e to the minus t over 12 plus c. If we choose a constant a to be e to the c, we can then write that as a e to the minus t over 12. And t equals 20 plus a e to the minus t over 12 is our general solution. Let us find a particular solution by revisiting the conditions we were given. We know that at t equals 0, t equals 80. Thus we can write that 80 equals 20 plus a e to the 0. Since we know that any number to the 0 is 1, this is 20 plus a, and hence a must be 60. Thus t equal to 20 plus 60 e to the minus t over 12 is our particular solution. Brief reminder, see we use the separation of variables, and then we've used the conditions we were given to work out the k value and then the a value. So now we can finally answer the question of how long it will take the coffee to cool by 20 degrees C. So if T was initially 80 and it's cooled by 20, it will now be 60. So substituting that in, we can solve for T. So e to the minus t over 12 will be 60 minus 20 all over 60, which is 2/3. And then t will be minus 12 natural log of 2/3, or about 4.87 minutes to 3 significant figures. We can show this on the graph. Obviously, you could make that quite accurate if you wish to. And we should note that the long-term behaviour in terms of the coffee temperature dropping is that it will cool down to the limit of the room temperature at 20 degrees C. So that line T equals 20 will be the limiting asymptote on the graph. In the next video, we consider multiplying by an integrating factor to give a perfect derivative as a technique for dealing with first-order differential equations.